Okay, so a little bit more revision. So we've been talking about forces that cause motion in a straight line. What did we call those forces? Two names. Push and pull, right? That was it. So the two forces that causes things to go in a straight line are push or pull. There is just a third kind of force that causes things to rotate. What's that force called?
Twist.
No, it starts with a T, but it's not twist. Torque, right? So think of torque as just a force that causes an object to twist. That's what it is. So a torque is nothing other than a force that causes an object to twist. That is not an official definition, but that's what I would like you to think about it. I would like you to think that. You can also call it a force that causes turning about a pivot, right? So what that means is it has to have, and the symbol for torque is usually written like this, like that tau, and it is defined as R cross F. It is a cross product. Two vectors are getting multiplied. And it is a cross product, so the answer should be a vector or scalar. So the answer will be a vector product. It's a vector product. So torque itself must be a vector. So what's the definition of a vector? It has to have a magnitude and a direction. Can you all take out your coordinate systems if you have them with you? Can we all take them out? Is this your coordinate system?
Yeah.
What is this axis that's coming towards your head? Okay, so or your shoulders or your stomach. What direction is that? What direction are you calling that? X. What is this then?
Y.
Y. And what is this then?
Z.
Where does Z point?
Up.
Okay, we got it. Okay, so now let's consider this point on the XY plane. Same thing. Okay, so now put that point, no, actually put that point, but in your head, put that point there. Now with your other hand, push it with a finger or something, right? So that push force, I'm gonna call it something else. That force that you are applying to this point P is a vector force, okay? Because you have a vector R that goes from your origin to the point that you chose, plus what you're pushing with. So now if you're in a right-handed coordinate system, so hold up your right-handed coordinate systems. This is R, this is F. What's the direction of your torque? Straight up, get it? So now if you hold this towards your R in your coordinate systems and push with this finger, like point it, like try to push this point away, your torque will be towards the ceiling. Get it? So your torque will always be a vector quantity. Yes, it's the right hand rule. Yep, cross multiplication is the right hand rule because we just did the right hand rule without calling it the right hand rule, but it is a right hand rule, right? And this R in textbooks is usually called the moment arm. And so the definition, the torque is a cross product of the moment arm and the force. But all it is a force that causes something to twist or turn. That's what it is. Which means I can write it as that, where phi is the angle between R and F. So what's the angle between R and F? If this is my F and this is my R, what's the angle between them?
90 degrees.
Well, yeah, in my case it's 90, but imagine if it's not 90. If I drew better, it won't be 90. But yes, you're right, it's close to 90. It can also be written as IJK matrices, X, Y, Z, and the components of F along X, Y, and Z, yes? Where R is a vector given by X, Y, Z, and F is a vector given by Fx, Fy, and Fz. Now, what about the work done? So what's the normal definition of work? Force times displacement, or force times dr. But now our object is causing a rotation. What's the distance my object is traveling? It travels a distance defined by the angle. When you have a linear motion, you get defined by the x displacement. But if you're twisting, what's the definition of how far you went? Depends on the angle. Actually, I should probably make it clear that you have to integrate over the angle from any phi1 to any phi2. Similar to kinetic energy, when we were going in a straight line, we called it 1/2 mv squared. How does that change for rotational motion? Kinetic energy rotational was 1/2 I omega squared, where I is the moment of inertia, and the moment of inertia depends on what kind of symmetry you're dealing with. And omega is angular velocity given by v equals r omega. V is the linear, omega is the angular. And the way I generally remember this is the only thing I remember is S equals R phi. And then take the first derivative to give you the second one, and take the second derivative to give you R alpha. Anyone remember the definition of power? Joules per second. So delta W over delta T. Or we also did it as F dot V. Do you remember deriving that last week? No? Nobody remember? I mean, it's simple. We could do it again. It's just F dot delta X over delta T, which was F dot V. So for rotational, can anyone predict what it would be? What's the force called in rotation? Torque. And what's the V called in rotation? Okay, now let's write Newton's law for, okay, so what is Newton's second law in linear? Think of what it would be for rotational. How did we define force in rotation? What did we call it? Torque. So what should be on the left side? Sigma should stay the same, but force will become torque. What did we define the mass as? Look at it here. The mass became moment of inertia. So take a wild guess what m will become when we are on this side for rotation. Moment of inertia. And what does a become for when you're talking about turning? See how that sort of follows the same pattern? It's like we're not doing anything new. We're just redefining, and we're redefining and keeping things simple, right? Okay, next one. We also said, Newton's second law said that the sum of the forces equals force 1 plus force 2 plus force 3 and so on. Is that what we've been doing for Newton's laws? Yes? Yeah. We write all of the forces, and then at the end we say whether this is 0 or ma or mv squared over r, correct? Yeah. Okay, so what do you think the counter for that is for rotation? What did we call the force? Torque. So the counter for that is you find all the forces that are causing the torques, and then you put this side equals to either 0 or I alpha. See it? It's literally the same thing. However, so there is a fancy word, sigma torque equals 0. Okay? That is called the equilibrium condition. Oh, by the way, this very, very simple thing that I just told you is called the principle of moments. Because, hey, why not? Yeah, the sum of everything. This the thing that we wrote that I said was very simple, and it was a byproduct of going from Newton's laws in a straight line to causing rotation. There is a fancy word. It's called the principle of moments. Which, yes, there is a fancy word for it. It's torque, it's tau, but it's nothing other than just taking your force and making it into a twist. Bobbleheads, with me so far? Okay, very good.